In today's session, we study the effect of pulse shaping on data transmission. As we know, for band-limited channel, we have to use pulse shaping filters to control the spectrum occupied by the signal and to mitigate the intersimple interference. We will focus on Gaussian and raised cosine filters. And we will compare their performance using measurements like the spectrum, eye, and polar diagrams. Starting with Gaussian pulse shaping, we will see its effects in terms of spectrum utilization and ISI. We are asked to send an MSK signal with Gaussian pulse shaping. We can do this manually, but we have an option for GSM signal. So we can just pick it. We go to the same setup. We make sure that you have digital modulation on. In the setup, instead of going through these parameters here, we go to a quick setup and pick GSM. By default, it will pick MSK. And for filtering, Gaussian with 0.3 bandwidth time product. And the simple rate would be 270.8 kilo simples per second. We need also to adjust the signal amplitude minus 20 dBm. Let's pick it for power, and we have 460 megahertz antennas, so we can start transmitting now. At the receiver side, we make sure that we have the right center frequency, and a span of 1 megahertz is enough. Let's do some averaging of 300 snapshots, and here we see the signal, and we have some side loops here, as we see. Now we know that the bandwidth time product tells us the filter spread over the samples. The smaller the value of this product, the less the spectrum utilization will be. So, but I will have for sure interference. So let's change its value here. Let's go back to the filter setup. Let's pick 1 BT equal to 1, which corresponds to MSK. If I go back, I will see the side loops of the MSK. Now let's put some markers here on the null to null bandwidth. I will add a second marker somewhere here. Now let's reduce the value of the bandwidth time product to 0.1. Let's wait for the averaging, and as I see, I have less spectrum utilization. Now let's do some digital modulation measurements. We will see eye and polar diagrams. We go to measurement setup, and for the type we pick digital modulation. In digital modulation properties, you have again to adjust the demodulation properties and match them to those at the transmitter. Instead of going again through the details, you can preset to a GSM signal by going to this drop-down menu, and it will adjust the parameters by default, which are this simple rate, MSK modulation, and for filtering we have Gaussian with 0.3. Now, as we see here, let's just adjust these things here for a better view. As we see here, we have some ISI at 0.3, but we have less spectrum utilization, and we can see the ISI here in the eye diagram. Let's increase the value to 1, the bandwidth time product to 1. And back at the receiver, we see that we have almost no ISI here in the eye diagram and in the polar diagram. Make sure also you adjust this parameter here to 0.21 for a better measurements, as we see here. If we go for 0.1, for example, a very low value, and we set the value here again, 0.1, we see here we have ISI. We can see it clearly in the eye diagram and polar diagram. For peak to average power ratio measurements, let's go and change the modulation from MSK to QPSK. And for filtering, we will keep the Gaussian for sure, but let's start with 0.1 as a bandwidth time product. At the receiver side, I will go and choose CCDF, and as we see here, we have this measurements of the CCDF, which tells me the peak to average power ratio almost here. So let me just put a marker. Now I will stop the measurements. I will go back and change 0.1 to, let's go with 1, and back at the receiver I will start again, and we will see a significant drop in the peak to average power ratio as we see here. Now let's change the pulse shaping filter to root raised cosine. We go back to the VSG, and for filter select we choose root Nyquist, and back at the receiver we start the measurements again, and we see here we have higher peak to average power ratio. Let's reduce the filter roll-off factor to, for example, 0.2, and start the measurements again, and we have even higher peak to average power ratio. So we notice that the Gaussian pulse shaping in terms of peak to average power ratio has a better performance. The dynamic range can be seen also using the mean time signal here shown below. Now let's compare the power spectrums of both filters. So let me go back to spectrum. Now here I have the root Nyquist filter with alpha of 1. Let's see the occupied bandwidth by selecting this option here, and let's put a band, rulers, and as we see here, this is the occupied bandwidth. Let's go with Gaussian now, and with the product of 1. As we see here, we have somehow less occupied bandwidth, but we have more side loops. Let's reduce its value to 0.1, and back at the receiver, let's wait for the measurements to repeat again, and we have way much less occupied bandwidth, but remember we have ISI. Back to the Nyquist, let's go with a value of 0.2, for example, and as we see here, we have less occupied bandwidth compared with the Nyquist at a roll-off factor of 1. Now looking at the polar and dye diagrams for the root raised cosine filter, here I have 0.1 alpha factor, and we see here we have a higher dynamic range of the signal. Make sure in the measurement setup you adjust the filter alpha of the measurement filter to be the same as the one used at the transmitter. Now let's see alpha of 1, and here 1. So we have less dynamic range of the signal. Next we see the effect of the filter span. Here I am connected to the VSG using MATLAB by a code that will be provided to you by the TA. I just generate some random data, and I filter it using a root raised cosine filter. Then I create a very simple frame where we have the filtered samples and we append some zeros. Next we transmit using the same parameter, 460 MHz and minus 10 dBm power, and this is the IP address of the VSG. Now here I'm transmitting with a span of 16 samples. At the receiver side, here we have the received signal. Make sure at the measurement setup you match the parameters to each other. Here I'm using a sample rate of 125 kHz because here I have the sampling frequency of 1 mega and the samples per simple of 8. So the sample rate will be 1 mega over 8, which is 125 kilohertz. For filtering, again, we choose root raised cosine as a reference filter and as a matching filter, and alpha is 0.5 at both sides. Now at 16 we notice that there is no ISI. Now let's go down with 4, a span of 4, and start transmitting. Now at the receiver side here, I have no noticeable difference as we see here. Let's go down with a very low span of only one sample, and we wait for connection. Once it's connected, the frame will be sent repeatedly. And here at the receive side, I can see some ISI, both in eye diagram and polar diagram, because the truncation has affected the pulse shaping. Back to a span of 16 to see the effect of truncation on the spectrum. Here I have the received signal spectrum, and this is the occupied bandwidth. Let's put some rulers as we see here. Now I will go again with 4, span of 4, and send again. We wait for connection. Now at the receiver side, we notice that the occupied bandwidth is almost the same, but I have more side loops. Let's go with a span of 1. Here at the receiver side, we notice a severe effect of such truncation, where the occupied bandwidth is way much more and the side loops are much larger. Actually, with such truncation, the root raised cosine filter is not a root raised cosine filter anymore. Back to the web control of the VSG, we will see the effect of match filtering. In modulation, I will go to the filtering setup and I will pick a root raised cosine filter with roll-off factor of 0.5. At the receiver side, using digital modulation type of measurement, I will go to the properties and I will select the reference filter to be root raised cosine, but without matching, so the measurement filter will be a none. And as we see here, we have ISI in both polar and eye diagrams. If I select root raised cosine, I will remove this ISI because I have match filtering. Let's go back to none. There is no filtering at the receiver side. And at the transmitter side, let's pick Nyquist filter instead of root raised cosine. And here we see there is no ISI. But match filtering has an advantage at very low SNR values because it acts like a correlation. To see this, let's pick minus 50 dBm, for example, and we keep using the Nyquist filter here. And at the receiver side here, let's pick Nyquist filter. And as we see here, we have more noise for the received signal. If I choose to go with the root raised cosine at both sides, we notice that we get a better performance because we have match filtering at the receiver side.